Hello, my precious friends. I really hope that you are doing great. Welcome to today's class. It is our first lesson on the 10th topic of Form 4, which is called radioactivity. As usual, let me commence by giving the quote of the day, which states that your dream has no expiry date. Keep chasing it, no matter how impossible it might seem. We shall discuss that quote at the end of our class today. So today we are looking at radioactivity, and it is important to remember that radioactivity is simply emanating from a branch of physics which was called atomic physics. Remember, in our very first lesson in this particular channel, the lesson was actually called Introduction to Physics Lesson 1. So in that particular lesson, we discussed the 6 branches of physics. And of course, one of the branches of physics was called atomic physics. So radioactivity falls under this particular branch of physics, which is called atomic physics. Now, in that particular lesson, that is Introduction to Physics Lesson 1, we defined atomic physics as simply a branch of physics that deals with the behavior of the particles constituting the nucleus of an atom, and of course their resulting or their accompanying energy changes. So of course these particles that are found within the nucleus of an atom, we are simply talking of the protons and of course the neutrons. So what is radioactivity? So radioactivity is simply the spontaneous disintegration of the nucleus of unstable elements with simply emission of radiations. Then radioactive decay is simply a process by which an element changes into another element by emitting radiations from the nucleus of that particular atom. So these radiations that we are talking of, we have the 3 main types of radiations. One, we have what we call the alpha particles, denoted by this symbol here. Then of course we have the beta particles, and lastly we have what we call the gamma rays. So in this particular lesson, we are going to discuss the properties of each of these types of radiations, and of course see why they are adapted to their specific functions that we are going also to discuss under radioactivity. Then let's look at what we call the atomic structure. That is the structure of an atom. So we know that that is from electrostatics lesson 1. We actually discussed the structure of an atom. Of course, it is also a topic that we covered in this particular channel. We said that an atom has its nucleus, which consists of the protons and the neutrons. We said that the protons are usually positively charged. Then outside the atom, we have what we call the energy levels. So within the energy levels, we have the electrons, which are usually negatively charged. So the nucleus of an atom has specific number of protons and neutrons. Of course, the neutrons usually do not have any charge. That is, they are simply neutral. Then the number of protons in the nucleus is also called the atomic number, or simply say the proton number. So that means the atomic number can be equal to the proton number within the nucleus of a given atom. Then an atom X can be represented as shown in this particular symbol here. So if we have an atom X, then the superscript usually represents the mass number of that particular atom. Then of course the subscript usually represents the atomic number of that particular atom. And you are saying that the atomic number can be equal to the proton number. So for example, in this case, these X then superscript 10 and subscript 4 simply means that this particular atom X has its mass number being 10. So the mass number of this particular atom X is 10. Then of course the atomic number is actually 4. So you will be seeing this particular representation of atoms when we'll be looking at the nuclear reaction equations. Then it is also important to note that the sum of the number of protons and neutrons is simply called the mass number, or simply the nucleon number. Therefore, mathematically, we can say that the mass number of an atom is equals to the sum of the number of protons within that particular atom and, of course, the neutrons. Then because you have said that atomic number can be equal to the proton number, it also simply means that the mass number, or what we are calling the nucleon number, can be equal to atomic number plus the number of neutrons within the nucleus of that particular atom. Next, we look at the first type of radiation, which is called the alpha radiation, or simply the alpha particles. So an alpha particle is simply the nucleus of helium. Then we know from chemistry that the first element of the periodic table is usually helium. So we know that helium is usually denoted by He. Of course, it is positively charged with a charge of positive 2. So helium has a mass number of 4 and atomic number 2. Therefore, the properties of alpha particles will be closely related to the properties of helium. So let's look at the properties of alpha particles, or simply put, alpha radiations. And the first property is that alpha particles, they are usually positively charged. So they are positively charged because we are saying that alpha particle is simply the nucleus of helium, and you have just said that helium is usually positively charged with a charge of positive 2. So because helium is positively charged, it simply implies that alpha particles will always be positively charged. Then the second property of alpha particles is that they are heavy and slow moving. So they are usually more denser as compared to other types of radiations. Then the third property of alpha particles is that they are deflected by strong magnetic fields, and of course also deflected by strong electric field. So due to the fact that they are charged, they will always be deflected by both magnetic and electric fields. So let's start by looking at their deflection in a magnetic field. So here is a magnetic field which is of course moving into the paper, as denoted by the simple X. Remember, X simply means that the magnetic field is moving into the paper or into the screen for this particular case. So to find the direction in which alpha particles will deflect, we usually use the Fleming's left-hand rule, of course, which we looked at within 2 topics. One of the topics was actually electromagnetic induction. The other topic was actually magnetic effect of an electric current. We analyzed the Fleming's left-hand rule. So we said that the Fleming's left-hand rule stated that when the first finger, the second finger, and the thumb of the left hand are held mutually perpendicular to each other, such that the first finger points in the direction of the magnetic field, the second finger pointing in the direction of the current, then the thumb must point in the direction of motion. Therefore, I'm going to apply the Fleming's left-hand rule. So I want you to hold the fingers of your left hand, the first 2 fingers, mutually perpendicular to each other, and of course also perpendicular with the thumb. Then, because for this case we are using X, and X simply denotes that the magnetic field is moving into the paper, I want you to hold the first finger towards the screen of this particular video. Then of course you hold your second finger in the upward direction. Of course, the second finger represents the direction of the current. And for this case, we are holding the second finger in the upward direction simply because the alpha particles are simply getting emanated from this particular radium source. And remember that because the alpha particles are positively charged, we know that current will always move from the positive terminal towards the negative terminal. So because the alpha particles are moving from this particular radium source upward, it simply means that the direction of current will also be upward, because the direction of current will always be from the positive terminal. And because the alpha particles are positively charged, therefore the current is moving from the source of this radium source, then upward. So the current, you hold the second finger upward, then the thumb point it towards the screen. If you have held those first 2 fingers and the thumb mutually perpendicular to each other of your left hand, you realize that as long as the first finger is pointing into the screen, then the second finger pointing upward, then you realize that your thumb is actually pointing to the left. Actually, try it practically. Just take the left hand, then hold the first 2 fingers mutually at right angles, of course with the thumb. Then ensure the first finger is pointing into the screen, the second finger is pointing upward in the direction of the current. Then you realize the thumb will be pointing to the left. So of course the left simply means that is the direction that our alpha particle will deflect within a magnetic field. So you can see the alpha particle is deflecting to the left, showing that the direction of motion of the alpha particle will be to the left within this particular magnetic field. So then we also look at the deflection within an electric field. So for the case of electric field, we simply consider this particular diagram here. So because alpha particles are positively charged, they will be deflected towards the negative terminal within an electric field. Remember, unlike charges will always attract each other. So due to the fact that alpha particle is positively charged, it will be attracted to the negative terminal of a given electric field. Then the fourth property of alpha particles is that they produce more ionized particles along their path. So they produce more ionized particles because, one, they are heavy and they are moving slowly. So the slower they move, the more the air particles they are able to interact with, hence the more the ionized particles along their path. Then the last property of alpha particles is that they have low penetrating power, hence can be stopped by paper. So they have low penetrating power because they are heavy and therefore they are slow moving. So of course, if they are slow moving, that simply means that their ability to penetrate any material will be very low. So they are stopped by paper. So you can see this is our radioactive source. Then we have the alpha particles which have been stopped by a sheet of paper. Next, we look at the second type of radiation, which is called beta radiations, or simply beta particles. So a beta particle is simply an electron emitted from an atom. And of course, from electrostatics, we said that electrons are usually located within the energy levels of an atom. So a beta particle is simply represented by an electron E, of course, which has no mass number and has an atomic number of -1. So the properties of beta particles or beta radiations include, one, they are negatively charged electrons. So of course, a beta particle being represented by an electron, and we know that an electron is simply a negatively charged charge. So it simply follows that beta particles will naturally be negatively charged because electrons are usually negatively charged. Then, two, they are lighter as compared to the alpha particles. Yeah, alpha particles are usually more denser as compared to the beta particles, which are usually lighter or less dense as compared to the alpha particles. Then the third property is that beta particles have less ionizing power as compared to the alpha particles. And of course, the reason is because they usually move faster as compared to alpha particles. Remember, alpha particles have higher ionizing power because they move slower and therefore they are more denser. So the slower they move, the more they interact with the molecules or particles, hence charging them or ionizing them. But because the beta particles have less ionizing power, it's simply because of them being light. That simply means that they move relatively faster as compared to alpha particles. And the faster a particle moves, the lesser ionizing power it has because it has less time to interact with molecules on its way in order for it to ionize them. So beta particles have less ionizing power as compared to the alpha particles. Then the fourth property is that beta particles are deflected by strong magnetic fields and also strong electric field. Remember, if any particle has a charge, it will always be deflected in a magnetic or electric field. But if a particle lacks charges, then it won't have any effect as far as deflection is concerned in either a magnetic or an electric field. So let's look at the deflection of beta particles in a strong magnetic field. Again, in this particular case, we are using fields which are into the screen, denoted by this letter X. But the only change is that for the case of beta particles, remember we are saying that beta particles are simply electrons, and we know that electrons are negatively charged. So electrons will always move in a direction which is opposite to the direction of current, that is by convection. So because we are having beta particles moving from this radium source, so if beta particles are moving upward, it simply means electrons are moving upward, that is away from the radium source. And because the electrons move in a direction opposite to that of the current, it simply means that now the current will be moving towards the radium source. So electrons and current will always move in opposite direction. So current moves from the positive terminal towards the negative terminal, while electrons move from the negative terminal towards the positive terminal. So because beta particles are simply electrons and the electrons are moving from the radium source, it simply means the current is moving towards the radium source. So using the Fleming's left hand rule, of course, you hold your first two fingers and the thumb of your left hand mutually perpendicular to each other. Then you ensure that the first finger points in the direction of the current. In this case, the current is moving towards the source of these particular beta particles, because the electrons are moving away from the source, because the electrons are simply the beta particles. Therefore, if the current is moving towards this particular source, ensure that the second finger points downward. So the second finger of your left hand, which is held mutually at right angles with the thumb and of course the first finger, then the first finger will move towards the screen. So point the first finger towards the screen, because that is where the magnetic field is moving towards, as represented by letter X. So if your first finger is pointing towards the screen, then the second finger pointing downwards towards the radium source, then you realize that your thumb is pointing to the right, showing you that the beta particle is going to deflect to the right. That is why we are having the beta particle deflecting towards the right hand direction, as shown in this particular diagram. Remember, the purpose of thick lead box is simply to absorb any stray radiations coming from the radium source. Remember, lead absorbs most of in fact, all the radiations. That is the alpha, the beta, and also the gamma rays. Then the fourth property of beta particles is that they penetrate through paper but are stopped by thin aluminium. So you can see we have an aluminium foil here, which is actually stopping these particular beta particles. Then of course we have said that beta particles are also deflected in a magnetic field. So because beta particles are simply negatively charged, or are simply electrons, they will always be attracted towards the positive terminal. Remember, unlike charges will always attract each other. That is why negative charges, or the beta particles, will always be attracted to the positive terminal of an electric field, because unlike charges attract each other. So beta particle being simply electrons, they will be attracted to the positive terminal of an electric field. So you can see we have another particle which is going up to the lead box. Of course, that will be the gamma ray that we'll discuss in our next slide. Next, we look at the third and the last type of radiation, which is called the gamma radiations, or simply put, the gamma rays. So what are gamma rays? So gamma rays are simply electromagnetic waves with very short wavelength and very high frequencies. So remember, we defined electromagnetic waves in Form 2 under a topic called Waves 1, whereby we said that electromagnetic waves are those waves that do not need any material medium in order for them to be transmitted. Then, if gamma rays have very short wavelength and very high frequencies, remember, from V is equals to F lambda, the higher the frequency, the higher the velocity of that particular ray. So if they have very high frequencies, it simply means that the velocity of this particular gamma rays will be very high, and therefore they will always have a very high penetrating power as compared to other types of radiations. So we look at the properties of gamma rays, and the first property is that they have no mass and therefore no charge. So they are not charged. So that simply means that we do not expect them to have any deflection within either a magnetic or an electric field. Then they are electromagnetic waves, simply means that they do not need any material medium for them to be transmitted. The third property is that they are not deflected by both magnetic and electric field. The reason being they have no charge. So for example, you can see here we have our radium source, which is producing these particular particles, or the rays. So when these rays flow through this particular magnetic field, they are not deflected in any direction. Instead, they continue moving in a straight path. So the reason is because they do not have any charge, and therefore they are not deflected either in a magnetic or an electric field. So similarly, you can see in an electric field, we have the positive terminal here, then we have the negative terminal, but the gamma rays are actually passing and deviated. So they are not deflected within either a magnetic or an electric field. The reason being they have no charge. Remember, it is the charge that will cause the deflection of a given ray within either a magnetic or an electric field. The fourth property is that gamma rays, they cause little ionization. So the reason is because, remember, we have said that they have very high frequencies. So that simply means that they move at very high speed. So the higher the speed they move with, the lesser the ionizing power, because that simply means that the time that they have to be in contact with the molecules on their way to be ionized is very, very little. That is why they have very little ionization power. Then the last property is that they penetrate through paper and aluminium but are stopped by thick lead. So in comparison to the beta particles and also the alpha particles, actually the gamma rays have a very high penetrating power. That is why they are able to go through a thin sheet of paper that was actually stopping our alpha particles. They are also able to go through aluminium foil, which was stopping our beta particles. So you can see that they are only stopped by lead block, and that is the reason why you can see here we have thick lead box. So the source of the waves is stored in a thick lead box to absorb any stray X-rays, because it will not allow any radiations actually to move out of this particular box in an expected way or in stray path. So they have very high penetrating powers. So as you can see, they are bypassing the sheet of paper. They are also bypassing aluminium, but they are only stopped by lead block. Lastly, I have an exercise that I recommend you should try at your own free time to get the understanding of the concepts that we've just learned. Of course, if you have any challenges in handling any of the questions, feel free to drop a comment specifying the question that you need help in. And as usual, I'm always here to try and help where possible. So we've come to the end of our class today, but we need to discuss the quote of the day. The quote of the day stated that your dream has no expiry date. Keep chasing it, no matter how impossible it might seem. So the quote is simply encouraging us not to fall in the trap of allowing timelines to dictate our dreams. Remember that the only variable to success is your willingness to put in the work. There are several examples of people who started working on their dreams at an older age and still became successful. Therefore, there is never a bad time to start doing the right thing. Just in the same way, there is never a good time to start doing the wrong thing. And lastly, recall that you are not lost. Instead, you are just early in the process. Keep pushing, never give up. Thank you very much for accompanying me until the end of this particular lesson. I do not take it for granted. In case you are new to the channel, kindly hit the subscription button and also turn on the notification bell so that whenever I upload a new video, you'll get notified. Until next time, this is Kind Tuition Academy. Thank you very much.